number of photons increases, then number of electrons also increases. Okay, number of electrons also increases. If the number of electrons is increasing, I can say current value. What is current value? Ne divided by T. What is N? Number of electrons. E, charge of electrons. Number of electrons is increasing, so current also increases. So from here we are coming back to relation. What is that? Intensity increases, current increases. Intensity increases with time. This current value, what current? We call it as photocurrent. That photocurrent also increases with time. When intensity increases, photocurrent also increases with time. And vice versa is also possible if we decrease the intensity at constant frequency. This should happen at constant frequency. Okay, intensity decreases, intensity decreases, then what happens? Current also decreases, provided all of this process is happening when the frequency mu is greater than threshold frequency and lambda is less than threshold wavelength. Remember this. Okay, this process should happen when this condition has to be satisfied. Next is frequency. What is frequency? The frequency, if you talk about the energy of the photon, what is energy of the photon? That is h mu naught plus k max. And if I solve this, energy of the photon equals to h mu naught plus k max. What is k max? ev naught. So from here we can write energy of the photon. What is energy of the photon? I am writing this. That is h into mu. So this h into mu is equals to h mu naught plus ev naught, or h into mu is equals to h mu naught plus k max. So in this case, how the energy of the photon? So how the energy of the photon depends. So here energy of the photon mu. So mu increases. This k max will also increases. If k max increases, then v naught also increases. It will become more, magnitude will increase. So mu increases, kinetic energy will increase. Mu does not have any effect on this current. Okay, mu does not have effect on the current, and at the same time intensity does not have effect on maximum kinetic energy and potential, stopping potential. Remember this line. These variables has nothing to do with that variable, and those variable has nothing to do with this variable. This thing that we should keep in mind. So frequency increases, maximum kinetic energy increases, stopping potential also increases. If frequency decreases, then maximum kinetic energy decreases, then stopping potential also decreases. Okay, stopping potential also decreases. So these are the things that we have in photoelectric effect. Let's see the graph. So I just told you, photocurrent is directly proportional to intensity. The graph will be straight line, parallel, straight line passing through origin, because both are directly proportional like this. Second, we have if you talk about the photocurrent versus stopping potential. If you plot the graph, initially at stopping potential current value will be 0, then again it will keep on increasing. It will increase to maximum value, that is we call it as saturation current, at which all the electrons has been ejected from the surface. So this one is saturated current. So this one is defined for only one frequency, only one frequency. Now if we talk about this, we can check there are three intensities, I1, I2 and I3. Current value, if we talk about I3 is greater than I2 is greater than I1. So these are the current value. So from here, this particular graph is plotted for different intensities but the same frequencies, because stopping potential for this one is same, that is V0. So this graph, I will be writing this same frequency but for different intensities. Okay, same frequency but different intensities. So just focus on the stopping potential. One value of stopping potential is there. So this will be different intensities, right? And this particular graph, this one, current is given by this. So corresponding intensities of the light will also be greater than like this. I3 will be more than I2 will be more than I1. So these are the three graphs we have. Next we have this. This particular graph is plotted for, you can check that saturation current value is same. So I is same. If I is same, means intensity is same. So this graph says that intensity of all the lights is same, but we have different colors of the light, different wavelengths of the light, because different frequencies of the light, because they have different stopping potentials. So this graph is different frequencies, but same intensity. same intensity. Okay, same intensity. Why same intensity? Because saturation current value is same. And last part that we have here, the metal A and metal B, we are plotting this V0 versus frequency. What is V0? Stopping potential. So here we will be writing this H mu is equals to H mu0 plus, if you write in terms of this, H mu is equals to, I can write here H mu is equals to phi naught Einstein photoelectric plus EV0. So this EV0, I'll be writing this. What is EV0? H mu minus phi naught. So what is V0? The V0 is given by H by E into mu minus phi naught by E. So this particular term that we have, the Y is equals to mx plus c. Okay, and what is the m here? The slope is given by m equals to h by e, comparing this. Okay, and y is V0 and c is the phi naught by e. So c is equals to phi naught by e, and that too minus. So this y-intercept of this graph, the y-intercept of this graph will give us the value of the work function for the given metal. So this y-intercept phi a by e, this is for metal A. So this y-intercept will give us phi a by e, that is work function of this, and this y-intercept will give us phi b by e, that is the work function for metal B. This will give a threshold frequency of metal A, and this will give threshold frequency of metal B. Both will be having same slope because slope is h by e. Okay. So let's solve some of the questions that we have. First, if this is the velocity of light in free space, the correct statement about the photon among the following is given by energy of the photon is h mu into mu. This statement is correct. The velocity of the photon is c. Okay, this statement is also correct. The momentum of the photon is given by h mu by c. This statement is also correct over here. The momentum of photon is h mu by c. In a photon electric collision, the total energy and total momentum are conserved. Total energy and total momentum are conserved. This statement also correct over here. This one is also correct. The photon possesses positive charge. Photon is neutral. So answer is of this A, B, C and D. So this energy of the photon, velocity of the photon, everything is. The momentum of the photon is E by C, that is H by E. This one is also correct. Okay. So this one is A, B, C, D, all are correct. Next we have this one. The number of photons per second on an average emitted by source of monochromatic light of wavelength 600 nanometer when it delivers a power of, so they have given the power and they are asking number of photons. What is power? Energy by time, energy of the light divided by time. Okay, power is energy of the light divided by time. So what is energy of the light? NHC divided by lambda. Okay, NHC divided by lambda divided by time. So what they are asking, number of photons per unit time, that is given by how much? N by T value. From here I can write here P lambda divided by HC. Put the values. What is P? What is P? Here we have 3.3 into 10 to the power minus 3 into lambda. What is lambda value we have? Lambda is 600 nanometers. So 600 into 10 to the power minus 9 divided by this. H value 6.6 into 10 to the power minus 34 into C value 3 into 10 to the power 8. So this one is 1, this one is 2. Okay. So this one is 2, this will be 100. So how much you got? Everything we are getting 10 to the power something. Let's calculate this. 10 to the power minus 9, 12. This is 10 to the power minus 10, and this is 10 to the power minus 10 divided by this 10 to the power minus 26. So we are getting 10 to the power 16. We are getting. So answer is 10 to the power 16 number of photons per second. So light with an average flux go on the unit. What is the unit? 20 watt per centimeter. 20 watt per centimeter square. So this unit that we are writing, 20 watt per centimeter square. So 20 watt per centimeter square is the watt is the power, and this centimeter square is the area. So power by area is the intensity. And what they're asking, energy. What is energy? How we can write intensity with energy? Energy divided by area divided by time. So what is energy? What is energy? Intensity multiplied by area multiplied by time. That's it. That's it. Nothing more. So this side we can write here energy. What is energy? Intensity. What is intensity? 20 watt per centimeter square. That is 10 to the power minus 4 into area. What is area? How much area they mentioned? 20 centimeter square. Oh, we should not have written this 20 into 10 to the power minus 4 into, in how much time? 1 minute. So 60 seconds. That's it. So this one is how much? 400 multiplied by 60. We are getting how much? 24,000. So 24 into 10 to the power 3 joule. That will be the energy. That will be the formula over here. Question number, next question is coming from the graph, that is photoelectric effect. So here the graph is given. This graph is given. That is, this is for C, and this graph is for B, and this graph is for A. We can check A and B are having same stopping potential. A and B are having same stopping potential. A and B should have same frequency, because A and B same stopping potential, same V naught, so it should be having same frequency. Remember this. Okay. Next, discuss this B and C. What is B and C? B and C are having same saturation current. This will be same I, so this will be having same intensity. Okay, same intensity. So what are the options we have? A and B will have different intensities. A and B will have different intensities. Yes, correct. A and B will have different intensities. They are having same frequency, different intensities. Intensities are different, right? While B and C will have different frequencies. B and C will have different frequencies. This is also correct. This will have different frequencies. Okay. B and C will have different frequencies because B is having stopping potential. This one, C is having stopping potential difference. This is also correct. B and C will have different intensities. No, B and C will have same intensities. I told you. No need to read further. A and B will have different intensities. A and B will have different intensities. Yes. While A and C will have equal frequencies. No. A and C cannot have equal frequencies because they are not having equal potential, stopping potential. So this statement is wrong. Remaining, B and C will have equal intensities. B and C have equal intensities, and A and B will have same frequency. Yes. Answer is A and B. No worry, just for practice question. Multiple correct is not there, but this A and B is the correct answer over here. Just for practice, we are doing this. Next, if the phi is the work function of the photosensitive material in electronic pole and light of wavelength of the numerical value lambda equals to hc by E meter is incident on it with above its threshold value at an instant, then the maximum kinetic energy of the photoelectron is rejected by it is given by. So what is Einstein photoelectric equation? Energy of the photon is equals to work function plus k max. Okay, and what they are asking? Light of wavelength. So if you write in terms of the wavelength, what is wavelength? hc by lambda in terms of the energy of the light and the photons of the wavelength is equals to phi naught plus k max. Okay, so is incident on it with energy above its threshold value at an instant, then the maximum kinetic energy of the photoelectron ejected by it at that instant is given by. So this particular things we have to write the value of the lambda. What is value of the lambda? hc by E. So let's calculate that. hc divided by hc by E, okay, is equals to phi naught plus k max. So this getting cancelled. We are getting this E. What is E is equals to phi naught plus k max. What they are asking? Maximum kinetic energy of the photoelectrons. So this k max they are asking. What is k max? E minus phi. Okay, E minus phi. Answer is option C. So moving to next question over here. The work function of cesium, potassium. So cesium, potassium and calcium. So cesium they have mentioned. So this one is this side cesium, this side we have potassium, and this side we have sodium. Work function they have mentioned how much? 2.14, 2.30. This is 2.14 and this is 2.30, and next we have 2.75. This is the work function that we have. Okay. So what is they asking? If the incident electromagnetic radiation has the incident energy of 2.2, the energy of the photon is how much? 2.2 electronic volt. Which of these photosensitive surface may emit the electrons? Okay, may emit the electrons. I said energy of the photons should be more than work function, then electrons will be emitted. Okay, then electrons will be emitted, then photoelectric is possible. Out of this one and this one, which one is possible? Energy is supply is how much? 2.2, and this requires 2.14. This will emit the electrons, but not about this one and this one, because this value is less. The work function is less than this. So answer is option D, that is cesium only. Clear? A light rays having the photons of energy 4.2 electronic volt are falling on a metal surface having the work function of how much? Having the work function of 2.2 electronic volt. what they're asking, the stopping potential of the surface is given by. So what is stopping potential of the surface? We can write the formula, that is energy of the photon. And what is energy of the photon? Is equals to phi naught plus ev naught. So from this particular calculation we can write, having photons of energy how much? 4.2 electronic volt is equals to phi naught. What is phi naught? Work function is 2.2 plus this one is ev naught. So what is ev naught value? We are getting how much? That is 2 electronic volt. And if they're asking stopping potential, that will be 2 volt. Corresponding stopping potential, we have to just cut the E over here. Corresponding stopping potential, this will be how much? 2 volt with the correct option over here. Next we have photoelectric effect threshold frequency question over here. If the threshold frequency of photoelectric metal is V0, if the light of frequency 4 V0 is incident on this metal, then maximum kinetic energy of emitted electrons will be how much? So we know energy of the photons is equals to phi naught plus k max. Okay, phi naught plus k max. What is energy of the photon that we will be writing? How much we have? How much energy is incident? This one. H into 4 mu naught is incident is equals to, what is work function? The work function is given by how much? How can you calculate the work function? We have the relation between the work function and threshold frequency, that is H into mu naught. So this particular time, that is H into mu naught plus k max. So from here I will be writing this 4H mu naught is equals to H mu naught plus k max. And what is k max? The k max value will be given by, that is 3H mu naught. Answer is option D. Clear? Answer is option D. When two monoactive lights of frequency mu and mu by 2 are incident on a photoelectric metal, their stopping potential becomes Vs by 2 and Vs respectively. The threshold frequency for this metal is given by. Threshold frequency for this metal should be given by. So what should be threshold frequency in this case? So what is the frequency? Lights of frequency mu, and this frequency is mu by 2. So threshold frequency in this case will be given by, that is H mu is equals to, we will be writing this H mu naught plus H mu naught plus, we will be writing this stopping potential. What is that? EVS. The case one, in the case one we have, stopping frequency is mu, corresponding potential is Vs by 2. And a photoelectric, their stopping potential becomes Vs by 2 and Vs respectively. Okay. The threshold frequency for this metal is given by. Second is H mu by 2 is equal to this side H mu naught plus E Vs by 2. So I'll be solving this. E Vs equals to H mu minus H mu naught, and this side E Vs by 2 is equals to H mu by 2 minus H mu naught. Okay. So this will be H mu naught. So dividing this equation 1 and this is equation 2, we'll be getting this. We'll be getting equation 1 by equation 2. We'll be getting this 2. So from 2 we can write here H cancel. So this mu minus mu naught is equals to mu by 2 minus mu naught. So this will go that side. So this is mu minus 2 mu naught is equals to this side mu minus mu naught. So how much we are getting this? This particular term will come this way. This is mu minus 2 mu naught. So from here, just a second, mu minus mu naught equals to mu by 2 minus mu naught. We'll be getting this, will come this way, mu minus 2 mu naught is equals to mu minus mu naught. So from here, what you want to find? Mu naught we have to find. So this equation 1, this is equation 2. So this particular term we are getting this mu. So from here we are getting this 3 mu naught is equals to 0 we are getting here. Just a second. So this so from here we are getting threshold frequency to be 0. Okay. So anyway, this particular questions. So anyway, I think this We can solve it using this. So we have to solve this equation and this equation over here, and we can proceed as the requirement, because we have to find the mu naught value from here. Okay. Light of frequency 1.5 times the threshold frequency mu is incident on a photosensitive material. What will be the photoelectric current if the frequency is half and intensity is doubled? Frequency is half and intensity is double. See, so what is threshold frequency? Suppose threshold frequency is mu naught. When we are applying the frequency 1.5 mu naught, this frequency is greater than threshold frequency. So when this frequency is greater than threshold frequency, photoelectric effect is possible. But suppose if the frequency is half of this, so what is new frequency? That is mu dash is 1.5 mu naught divided by 2, that is 0.75 mu naught if the frequency is half of this. This frequency mu dash has become less than threshold frequency now. In this case, photoelectric effect is not possible. So no matter whatever the intensity you are getting double, the photoelectric effect will not be observed. So what is photoelectric current will be 0. So initially threshold frequency is mu naught, and what is applied frequency 1.5 mu naught, that is greater than mu naught. Now we are reducing it by 2 times, so this will become 0.75, and this particular value is less than this threshold frequency. In that case, it will be 0. So when the light of frequency 2 mu naught is incident on metal plate, the maximum velocity of electron emitted is v1. When the frequency of the incident radiance is increased to 5 mu naught, the maximum velocity of electrons emitted from the same plate is v2. The ratio of v1 to v2. So first the case one will be writing this. What is frequency? Mu1 equals to 2 mu naught. What is the maximum velocity of electrons emitted here? So v max, that in this case that is v max 1. V max is v1. So I'll be writing this h into mu1 is equals to this h into 2 mu naught is equals to this phi naught plus k max 1. Okay, phi naught plus k max 1. What is case 2 of the question over here? Case 2 of the question, what is happening here? When the frequency of the incident radiation is 5 mu naught. So what is frequency now? The frequency is now 5 mu naught. What is the maximum velocity is v2. Okay, the maximum velocity in this case is v2. So if I write the Einstein photoelectric equation here, h into phi mu naught is equals to this phi naught plus k max 2. Phi naught plus k max 2. And what is threshold frequency? Threshold frequency is mu naught. So this particular term, that is 2h mu naught is equals to h mu naught plus k max 1. So what is k max 1 we are getting from here? The k max we are getting from here is h mu into mu naught only. And this side here we have this side phi h mu naught. Phi h mu naught is equals to this phi naught. What is phi naught? 2h mu naught h into mu naught plus k max 2. What is k max 2 that we are getting from here? So k max 2 that we are getting from here is that 4h mu naught. So what is the relation that we will be getting here? K max 1 divided by k max 2. So k max 1 divided by k max 2. So h mu naught divided by 4h mu naught, we are getting this 1 by 4, that is v1 by v2 ka whole square, because this is kinetic energy, v1 by v2 ka whole square. So from here we can write that is v1 by v2 is equals to 1 by 2. Answer is 1:2. Photons with energy of 5 electronic volt are incident on a cathode C in a photoelectric cell. The maximum kinetic energy of emitted photon is 2 electronic volt. When the photons of energy electron are incident on it, the photon will reach the anode if the stopping potentials. First one is that energy of the photon. We are using the same formula, that is energy of the photons. So what is energy of the photons? Energy of the photon is given by photons energy is given by this phi naught plus EV naught in terms of the stopping potential we have. So what is energy of the photon? Here we have 5 electronic volt, and what is this phi naught we have to calculate, and the maximum kinetic energy of the photon emitted is 2 electronic volt. This is also K max also we can write. So in this case the 5 electronic volt is equals to phi naught plus 2 electronic volt. So what is phi naught? We are having this 3 electronic volt, that is the phi naught we have. Suppose when the photons of energy 6 electron volt incident on C, no photoelectrons will reach the anode A. So in this case energy of the photons is equals to again the same formula phi naught plus EV naught. When the photons of energy 6 electronic volt, so here the energy is 6 electronic volt are incident on C. What is work function? What is work function here? Work function we got from here, that is 3 electronic volt plus EV naught. So from what is stopping potential we are getting here? 3 volt. Incident on C, no photoelectrons will reach the anode A if the stopping potential of A relative to C is how much? Answer is -3 we have to take, because I told you that anode will be always negative. Anode will be negative. So this stopping potential will be writing this -3 volt. Okay. A source of light is placed at distance 50 cm from the photocell. 50 cm from the photocell. The stopping potential is V0. So this is the photocell we are keeping over here. If the distance between the light source and photocell is made 25 cm. So if you are making this bulb over now, initially 50 cm, so finally how much? 25 cm. What will change and what will not change? Frequency will not change, intensity will change. Intensity will increase because we are placing this particular bulb closer to this cell. So intensity will increase, but what they're asking, new stopping potential. Stopping potential has nothing to do with frequency, intensity of the light. I told you, intensity of the light has nothing to do with the stopping potential, and vice versa we can say stopping potential will remain same. It only depends on the frequencies. It will remain same. Two radiations of photons of energy 1 electronic volt and 2.5 electronic volt successfully eliminate a photosensitive metallic work function 0.5 electronic volt. The ratio of the maximum speed of the emitted electrons in this case. So first one is h mu is equals to phi naught plus k max 1. Putting this value, 1 electronic volt is equals to this side. What is work function we have? 0.5 plus k max 1. So what is k max 1 we are getting from here? That is 0.5. This is the case number 1. Second is we are incidenting 2.5 electronic volt, and that is given by this how much? Phi naught plus k max 2. So what is 2.5 is equals to this side 0.5 plus k max 2 in the second case. So what is k max 2 we are getting here? That is the 2 electronic volt. So k max 1 divided by k max 2 is equals to V1 square by V2 square equals to 0.5 divided by 2, that is 1 by 4. If I take the root, so V1 by V2, that will be getting 1 raised to 2. Okay, that is 1 raised to 2. Answer is option B. When a monochromatic radiation of intensity I falls on a metal surface, the number of photoelectrons and their maximum kinetic energy are N and T respectively. So intensity is I, then number of photoelectrons, and in this case is N, and kinetic energy is T. Okay. If the intensity of the radiation is 2I, intensity I am doubling. So intensity is proportional to number. Intensity means number of photons. Number of photons is proportional to number of electrons. So photons and electrons are proportional. So in this case, number of photons, so number of electrons will also get double. This will become 2n. But what about the kinetic energy? Nothing to do with kinetic energy. It will remain same. So this will be kinetic energy will remain same because frequency is not changing. So this will be 2n and t respectively. Okay. So next we have de Broglie wavelength. So any electron which is So de Broglie wavelength, any particle which is moving with certain velocity will also be having wavelength. So that wavelength is given by lambda is equals to h by mv, or lambda is equals to h by p. And what is p? The p is given by p is given by this p first, that is p is the momentum. So momentum is given by p is equals to m into v. And second, if I write p is equals to, in terms of the kinetic energy, this is under root 2 mk. If you write this, p is equals to under root 2 m q into v. And what is kinetic energy? Q multiplied by v. If the charged particle accelerates through potential difference of v, then we're writing this v. So from here we can write lambda. What is lambda? H by mv. From here we can write lambda. What is lambda? H by under root 2 m kinetic energy. From here we can write lambda. What is lambda? H by under root 2 m q multiplied by v. If charged particle q is accelerated through a potential difference of v, then we are having this lambda value. Okay, h by under root qm divided by v. We also know that formula, that is r is equals to mv by qb in terms of width, in terms of the charged particle in moving in magnetic field, radius is given by this. So from here we can write here m into v is equals to qbr. So what is lambda from here? H divided by qbr. Okay, h divided by q by r, because h divided by mv. Next we have, that is lambda. So what is lambda? H by under root, we'll be writing this 2m kinetic energy. What is kinetic energy? 3 by 2 kBt. This lambda will define for gaseous molecules. Okay, this lambda will define for gaseous molecules. So what is this 3 by 2 kBt? This is the kinetic energy of the gaseous molecule, where T is the temperature. T will be temperature. Again, if we define for the neutron is defined as h divided by under root 2m kBt. What is kBt? The kBt is the energy of the neutron. Okay, what is T here? T will be temperature. So these are the different formulas we have for the de Broglie wavelength. So suppose if I pick up this one, that this particular formula, that is h, lambda is equals to h divided by under root 2 mq into v. If any charged particle is accelerated through a potential difference of v volt, then what is the lambda value? H by under root 2 mqv. So suppose for example, electrons we have, what is the charge of the electrons? 1.6 into 10 to the power minus 19. And what if the potential difference is v only? Potential difference is v. So for example, if writing only for electron, that is given by h divided by under root 2 mq into v. We know the h value, 6.6 into 10 to the power minus 34 divided by under root 2. Mass of the electron, m is the mass of the electron, 9.1 into 10 to the power minus 31. Charge 1.6 into 10 to the power minus 19 into potential difference is v. If any electron is accelerated through this much potential difference, so this entire value I will be summarizing and writing in short form, that is lambda is equals to 12.27 angstrom divided by root of v. And this value you should remember, this particular formula that you should remember for the wavelength of the electron which is accelerated through a potential difference of v volt. V is the potential difference. This is not only for electrons, we have for other particles also, like this. What is that? Lambda for this we have for the electrons 12.27 divided by root of v. For the protons 0.286 divided by root of v. For this deuteron 0.202 divided by root. What is deuteron? H12. It will be having 1 proton and plus 1 neutron. Okay, H12 deuteron. If we have lambda for this alpha particle, that is 0.10 divided by root of v. What is v everywhere? Potential difference through which it is accelerated. So this lambda for neutron, the neutron is given by lambda h divided by under root 2 m k into t. What is k here? Boltzmann's constant. The k is Boltzmann's constant. What is the value? The k value is given by T is the temperature. K value 1.38 into 10 to the power minus 23. Okay, this is the Boltzmann's constant. That is Joule per Kelvin. This is the Boltzmann's constant we have. So these are the different quantities we have, different particles we have, different wavelength. 0.286 by root of v, 12.27, and this one is 0.202 by root of v. This is 0.10 by root of v. So again, it depends on this. The parent formula is this one, that is h by p, h by 2m e, where e is the energy, and what is energy? E is equals to q into v. So let's see some of the questions from here. An electron and alpha particle are accelerated by the same potential difference. Let lambda E and lambda B denote the de Broglie wavelength of the electron and alpha particle respectively. So lambda depends on what? So we can check lambda is inversely proportional to all of these quantities. Whenever you're having graph of lambda versus any quantities, that is like this graph will be there. Lambda versus any other quantities, if they're asking any other quantities, okay, the graph will be like this. This is the lambda value, lambda versus any other quantities. Okay, so let's solving this question. So some of the questions that we have, lambda is given by h divided by under root 2mq multiplied by b. So in terms of the, if we compare the lambda of the proton and lambda of the electron and lambda of the alpha particle, lambda is inversely proportional to root of mass, root of charge, if they are having same potential difference. So lambda is inversely proportional to this. The one which is having higher mass will be having lower value. So we can directly say lambda of electron divided by lambda of alpha particle. Okay, lambda of alpha particle will be given by, so this directly we can qualitatively analyze and we can tell it mass of the electron will be more, so lambda will be less. Sorry, I'm telling opposite. The mass of electron will be less, so lambda will be more. If alpha particle mass is more, so lambda will be less. So lambda of E should be greater than lambda of alpha particle. The de Broglie wavelength associated with the electron accelerated by potential difference of 81 volt is given by. So what is de Broglie wavelength? Lambda is given by 12.27 divided by root of V. So this will be 12.27 divided by root of V. What is root of V? Root of 81. So this 12.27 divided by 81, we have 9. So approximately if I solving this 12.12 by 9, this we are getting this is in terms of the angstrom we have. If you write in terms of the nanometer, so this is in terms of the angstrom, 10 to the power minus, this is 12.27 10 to the power minus, so this one is 12.27 into 10 to the power minus 10 divided by 9 we have to do. So this I'll be writing this 1.227 divided by 9 into 10 to the power minus 9. In terms of the nanometer, this will be 0.136. If you solve this, 0.136 nanometer that will be getting. An electron of mass m moving with velocity v, then what is the velocity? V is given by v naught I cap, enters electric field. Electric field exists in which region? Let's check it. That is, electric field exists in this particular region, minus E naught. So this side electric field is this way. Okay, electric field is this way. Electron is entering this electric field. What is the force that is experiencing on this? The force will experience this side E multiplied by E, and because of this force, E multiplied by E. And what is the velocity in the same direction? Electric field is opposite direction, E multiplied by E naught. Because of this, there will be acceleration, mass into acceleration, Newton's second law. Mass into acceleration is E multiplied by E naught. So what is acceleration? We can write here E multiplied by E naught. So acceleration we can write here E multiplied by E naught divided by m. So what is V? U plus AT we have. So from here we can write directly V is equals to U plus AT. So V is equals to U. What is U? V naught plus acceleration. What is acceleration? E capital E naught divided by m into T. So case 1 of the question in which we have case 1. What is initial velocity? V naught. What is initial momentum? M V naught. What is lambda 1? H divided by m V naught. Case 2. Now the velocity after some time t has been changed, and what is the velocity now? The velocity is no longer the same. That is, the velocity v2 is, I'll be writing this v naught plus E capital E t divided by m. So what is p2? P2 is m v naught plus m E capital E t divided by m. M or m cancel over here. Suppose if I write m v naught common, okay, don't cancel this, we have to check, right? So this m v naught common, if I write this, so what we are getting? So if I take m v naught common, 1 plus m v naught common, okay, multiply by v naught and divide by v naught. So this side 1 plus E capital E divided by m v naught into t. This particular things we are getting. Okay, so this, what is lambda final here now? Lambda second, that is h divided by m v naught into 1 plus E capital E divided by m v naught into t. So this particular term is lambda naught. So what is lambda final? Lambda naught divided by this 1 plus E capital E divided by m v naught into t. So answer will be option A. Answer will be option A. When a metallic surface is limited with radiation of wavelength lambda, stopping potential is V. If the same surface is limited by radiation of wavelength 2 lambda, stopping potential is V by 4. The threshold wavelength of the metallic surface is given by, threshold wavelength for metallic surface will be given by. So here, okay, this particular thing is coming from the photoelectric effect only. So anyway, we'll solve it. This photoelectric effect, if we talk about, the question is the case 1. What is case 1 we have? What is the wavelength we have? Lambda. 1 is lambda. Stopping potential is V1 equals to V. So let's solve this. That is Hc by lambda is equals to threshold wavelength they're asking. So that is Hc by lambda naught plus Ev. Case 2 of the question over here. That is now what we have. The wavelength of the light is 2 lambda. And what is stopping potential? The stopping potential that we have is V by 4. Okay, that we have is by 4. So this Hc by 2 lambda is equals to Hc by lambda naught plus Ev by 4. Okay, Ev by 4. So solving this, we'll be writing Hc by lambda minus Hc by lambda naught is equals to E into V, equation 1. And this will be Hc by 2 lambda minus Hc by lambda naught equals to Ev by 4. This is equation 2. Equation 1 by equation 2. Quickly do equation 1 by equation 2. What we are getting from here? Equation 1 by equation 2, that will be getting 1 by 2 Hc by lambda minus Hc by lambda naught divided by Hc by twice lambda minus Hc by lambda naught is equals to this side Ev by 4, that is Ev divided by Ev by 4. So this particular term will be getting 4. So this Hc getting cancelled. So this will go that side. 1 by lambda minus 1 by lambda naught equals to 4 by 2 lambda minus 4 by lambda naught. Okay, so this things will come over here. We are getting this 4 by lambda naught minus 1 by lambda naught is equals to, this will go that side, 2 by lambda minus 1 by lambda. So this we are getting, that is 3 by lambda naught is equals to 2 by lambda. So what is lambda naught? The lambda naught we are getting here 3 lambda by 2. Clear? So that is the lambda naught we are getting here 3 lambda by 2. Threshold wavelength. Just a second. So this one is getting minus, this will come this side, this will become plus 1 by lambda minus 1 by lambda naught, 4 by 2 lambda minus 4 by lambda naught. This is Hc by lambda naught. So this one is Hc by lambda naught plus Ev by 4. This will become 4 times. So 1 by lambda minus 1 by lambda naught. This is 1 by 2 lambda minus 1 by this. So this will become 2 lambda here. And this is 2 lambda here. This is, we are getting, just a second. So 1 by lambda minus 1 by lambda naught is equal to this side 4 times of this 1 by 2 lambda minus 1 by lambda naught. So this we are getting 1 by lambda minus 1 by lambda naught equals to 2 by lambda minus 4 by lambda naught. So this term will be writing this. So this will be 3 by lambda we are having, 3 by lambda naught that we are having. This will go that side and this will come this side. So this will be having 2 by lambda naught. So from 2 by lambda. So what is this lambda naught value will be getting? That is 3 lambda by 2. Okay, 3 lambda by 2. Potential is V by 4. Wavelength of this is 2 lambda, right? If the kinetic energy of the particle is increased to 16 times its previous value, the percentage change in de Broglie wavelength. We have that relation lambda. What is lambda? H by under root 2m kinetic energy. If the kinetic energy is increased to 16 times, so initially let's say this is lambda. Lambda dash is equals to h by under root 2m. How many times? This is 16 times of this kinetic energy we are having. So this h by under root 2m kinetic energy, this is 16 times. So this will become how much? H by 16 will come outside. This will be 4, and this will be how much? 2m kinetic energy. So this particular term is lambda. So this particular term will be lambda divided by 4. Okay, lambda divided by 4. Percentage change in wavelength. What is percentage change? The percentage change that we'll be writing here. Lambda minus lambda by 4. What is initial? Lambda multiplied by 100%. Okay, so this we're getting here 3 lambda by 4 divided by lambda multiplied by 100%. So we're getting this 3 by 4 into 100. Lambda lambda cancel. Answer is 75%. Right. So this, let's solve this particular question. Last question of this. Electron of mass m and photon have energy E. Both are having same. That is, energy of the photon is equal to energy of the electron. Okay. The ratio of the de Broglie wavelengths associated with them is electron to lambda of electrons. I'll be writing this. What is lambda of electrons? H divided by under root 2m into energy. Okay. And what is lambda of the photon? What is lambda of the photons? We have, that is energy divided by C. We know this, that lambda is given by hc by lambda. Okay. This is momentum, sorry, this will be momentum. Or so this lambda of the electrons that will be having. So energy is equal to hc by lambda. So lambda of the photons, I'll be writing in that sense hc by E. Okay, hc by E. So this will be hc by E. We have to find the ratio of these two. So lambda of electrons divided by lambda of photon. So dividing this, if I divide this and this, h and h cancel, E will go up, E by C under root 2m into E. So this particular term we are getting, so this will be 1 by C under root E divided by 2m. So we are getting this particular term, that is 1 by C E divided by 2m p power. So this term that we are getting, the answer is option C. So this is what we have. Mostly the questions will be coming from the photoelectric effect, and second the question is coming from this dual nature of matter and radiation. In that we have the photoelectric effect, one possible where the question will be asked. Maximum question has been asked over the ES from the photoelectric effect, and second question will be coming from the de Broglie wavelength. These two topics is the must. That and photoelectric effect, different situations we have, different, like how intensities and frequency will depend on each other, how intensities and stopping potential, frequencies and corresponding intensities and current value will depend on each other. Those things we'll be discussing. Einstein photoelectric equation, maximum numerical question from the Einstein photoelectric equations. Next we have tomorrow that will be discussing this modern physics. Next topic is this atoms and nuclei. In the atoms, the major question is coming from Bohr model of an atom. In chemistry also you might have discussed a little bit. And in nuclei we'll be discussing that nuclear size, the size, nucleus density, the volume, area, surface area, nuclear force, what is nuclear force, strong nuclear force, weak nuclear force, and binding energy, mass defect. These are the topics that we'll be covering tomorrow in tomorrow's top topic. So till now you keep practicing more and more questions, and this time more revision is there, like focus on all the formula based revision. We'll see you tomorrow on this.